Thanks everyone for coming. We are Adam and Chris, and we're from the visualization team at Joby Aviation. And we're at a company that is making an electric vertical takeoff and landing aircraft like this. And the authors of hubble.gl, a JavaScript animation library in the VisGL suite. Both of us previously worked and collaborated with each other at Uber, alongside many of the talented individuals from the Uber Viz team. And today, we're going to delve into how we harness motion graphics techniques in combination with deck.gl and the VisGL suite to craft compelling narratives. So let's take a look at one of our most recent projects. So imagine this, 29 million trips happening every day here in New York City. At Joby, our vision is to alleviate this some of this traffic that this causes with the third dimension. We created an animation showcasing travel data and used this to show how our aircraft is designed to meet the demand criteria for our markets. It was displayed on this massive 25-foot screen in front of hundreds of folks at our latest aircraft launch event in June. As visualizers, our mission is to foster trust and credibility through data. Deck's flexible API, combined with everything that comes with the web platform, empowers us to convey intricate concepts with clarity. And with the turnaround time, that keeps our stakeholders happy. So let's walk through our creation process and discuss how you can adopt some of our techniques for your applications. So the first thing I want to focus on is dealing with time and animation. And then we'll cover rendering and video in the browser, and finally get into some of the directions we're hoping to take this work in the future in ways you can think about exploring alternative UIs for geospatial tools. Throughout, we'll share how we're rethinking hubble.gl to make it easier to get started, and how we want to make the experience of creating visuals a little more intuitive, even if you don't come from an animation background. Animation as an art form is a compelling way to tell your story. With it, you can capture your audience's focus and help them develop new ways of understanding the data around them. hubble.gl has always been a powerful animation tool, but up until this year, we limited our animations to short and simple clips due to how much time and effort they took to make, meaning they were useful mainly for quick insights and basic context. This year, we've developed a new framework that allows us to create longer, more complex animations in less time graphically. The biggest addition here is the interactive timeline and parameter UI component made with a library called Theater.js. And with this UI, we can instantly iterate on dozens of parameters and expose just the one we need to direct our scene. Now we have the capability to craft intricate, well-rounded, and interconnected storylines, fostering a deeper engagement and ensuring constant object constancy throughout, making them particularly valuable for complex narratives. One of the real benefits of this workflow is being able to control multiple data channels simultaneously in a rich and layered visual. And now we can make more immersive animations, such as when we mapped 10,000 miles of flight tests at the end of last year. Using Deck, we rendered out each of the 200+ flight tests as a blue and white trace on a grid. The challenge? Conveying that the abstract circles actually represent real-world flights without a lot of heavy text or voiceover. To bridge this gap, we used a plane icon and a map for context, but as it left behind a trace, like contrails, we faded out the map of the plane and introduced the rest of the traces into introduced the rest of the traces in a single camera move. The solution relied on object constancy to ensure legibility while also keeping the design clean and engaging. Few GIS tools offer us this level of flexibility, and few computer-generated imagery tools give us powerful georeference capabilities like vector tiles or GeoJSON, or allow us to collaborate in real time. While animated visuals draw attention quickly, their real magic is in simplifying complexity. Long-form animations in particular provide a consistent context, ensuring viewers grasp the full story. Our takeaway? Extended animations convey your message far more effectively than brief snippets. I'm going to hand it over to Adam now.
Cool. So I want to take a quick diversion to talk about some of the core principles of animation. We'll talk about the core primitives, then build back up to our higher level of abstraction. So I want to start with what is a keyframe, what is a timeline, and how do you smooth the values over time, which is what a graph editor is used for. And I want to talk about what is interpolation. So let's start with what is motion. It's movement over time. If you could stop the world at any point, that's what you'd see. It's the state of the world at a given moment. Think about it like taking a picture, and a video is a series of pictures. Animation is just reconstructing motion, adding that movement back in. So borrowing a page from classic animation, we want to describe our motion in terms of key poses at the extremes of the sequence. For deck, we can easily set the position, color, width, and opacity of key properties we want in a specific time within our timeline, and then fill in the gaps over time to help the animation land with the dramatic punch we need to help sell the narrative. For this next section, we'll use a free 3D software called Blender to help illustrate some examples. In this case, we want to show a bouncing ball. We'll first have to mark our key positions and the time in the sequence when they occur. So keyframes, as they're called, are represented as a diamond in the timeline. The moving blue bar is the playhead. When the playhead hits the keyframe, the ball's position is updated. We can move the keyframes to adjust the timing of the animation. So as jerky as this is, we already have the illusion of motion. So in traditional animations, you draw your key poses and then draw tweens between the keyframes to smooth the motion. Sometimes you want your animation to be fast and snappy for very exciting action, and other times you want it to be slow and methodical. How you draw those intermediate frames can really tell a story all its own. So because we're building everything procedurally, we can have the computer smoothly interpolate the value over time. We now have the illusion of motion. So taking a look at the timeline again, we see that we can move the playhead, and the value on the graph corresponds with the ball's position in space. In reality, it's the opposite. The playhead is what determines the ball's position. It's a linear function using the current frame as the input. So this is easy to implement in code, and it's often where programmers lead things. You just need a timer and a step size. In GLSL, this is interpolated as the mix function, and it's often used in fragment shaders. Linear interpolation is a great start, but it's rarely the best choice for motion. It leads to this stiff, robotic, and unnatural movement. Most objects in the real world don't act like this. So to make it a little smoother and more realistic, we can ease the curve, that is, mimicking something like friction, where an object takes a bit to get going, come to a stop, and faster in the middle. It's more pleasing to the eye because it feels more right. These are easy to drop into code and built into CSS or other libraries, for instance. But even with this improvement, this motion also feels unnatural. The default ease gives us this sine wave pattern, which is much nicer to look at, but still doesn't feel like a bouncing ball. Real bouncing balls have momentum and hang time. The graph itself is also editable. So just like Adobe Illustrator, we can use the Bezier handles on the graph editor, giving us precise control over the shape of the curve. Moving a handle further inward means the interpolated value will stay closer to the keyframe's value for longer. So building an animation this way allows for a much more precise control to dial in the motion. And often in your animations, you'll maybe want to speed ramp or to keep momentum over the course of a transition. Interactive editing gives you immediate feedback to try multiple ideas, which leads to faster turnaround times, happier stakeholders, and more polished outputs. It also allows you to inject a bit more personality into your motion. Notice how different the ball looks when it has a long time spent bouncing at the bottom versus how it looks when we spring back quickly. It changes how you think about the weight of the ball or the elasticity of the material. So maybe one feels more like a kickball and one feels more like a medicine ball. To sum it up, linear is good, easing is better, Bezier is best. Linear is easiest to implement in pure code. Easing, you often want to use a library function for, and Bezier curves usually leverage a graphic UI to help fine tune. So let's put it all together. We're going to revisit the example we started with. It serves as a practical demonstration of our methodology. So we gathered data from internal teams and public sources and presented this information in a single continuous narrative to draw the audience's attention to our core narrative and visually tie many parts of the story together. For instance, we start with the trips layer and then crossfade to arcs and then hexes using colors and the Kuleshov effect to visually associate those graphical marks with the same concepts. I also want you to notice how the values update in real time on the right sidebar as in response to the playhead position. Moving along the timeline, we'll update the derived properties in the easings graph. We can animate many other properties simultaneously, like colors or camera views or even filters on a data set like the min and max value. As long as there's a continuous differentiable domain, this technique proves really useful to us. We've modeled most properties that you might see on the deck layer as props exposed to us for faster iteration. When we see something we like, we can immediately test it out. The timing, dragging keyframes in or out to affect the sequence speed. In most deck apps, you'd interactively change these properties one by one using a slider or drop down with a mouse as your input control. But by tying them to a timeline, it allows us to layer the grammar as chorded combinations. It enables us to tell more complex stories and draw your attention to specific details. Usually we'll get a flurry of notes early on in the process, and we go through many iterations with our stakeholders. I think this is the 21st revision over 2 weeks. So being able to quickly iterate and respond to feedback is crucial to this line of work. This is an example of what we call a hero route. It's a common visualization we're called on to make for social and government operations. We demonstrate how much faster our airplane is than a car ride for the same trip. So storing the config values separate from the code lets us create many instances of the visualization type. Given that we may want a hero route for Dubai and one for NYC that share the same deck layers and general properties, but maybe different pickup and drop-off points or arc heights or specific colors to match a branded event. So let's do a demo flight from here at Foursquare HQ to JFK, hopefully sometime soon. So it's built on a GLB model for the airplane combined with 2 trip layers, one for the airplane and one for the car. And I'm just copying the lat longs from JFK into the config here. It can be helpful to think about these animations as a series of sequences layered together, creating a frame as the output. Here we're keyframing the camera and the aircraft simultaneously, plus animating the driving path over time as well. Just update the values, move the playhead, and then update the values again, and it'll insert a keyframe. Our aim is always clarity. This step-by-step layering helps audiences follow the narrative from the general overview to specific details. More specifically, we can interactively move the controls, and the keyframes will update with it. But one of the really nice things is that we can then use those properties to derive other properties. So we actually look at the first and last keyframes in order to decide where to put the arc. And also then we call out to the Mapbox Directions API, which means that anytime we update it, even as we're moving it around, the directions are correct for that output. This also allows us to use the easings graph here to update the arc. We can either create a video as an output or an interactive map, which is really quite nice. I mean, this took like 2 minutes to spin up one of these, but then, we can spend the time with our stakeholders iterating back and forth and deriving the props. So you can think more generally about building a frame as a pure function of state and time is just another input into the deck render. Some of the state gets pushed into layer props and some into state transformations like aggregations, joins, and API calls. And the result is painted onto the canvas. Since deck accepts props in the current state of the world, all we have to do is ensure our state reflects the values we want for that frame, and then deck will handle the rendering. So setting up one of these visuals is actually pretty straightforward. It simply becomes a matter of defining our object schema, which is used to set up the UI and define our parameters. And these generally tend to be a one-to-one between sheet object prop on the left and using it for a deck layer prop on the right, and then maybe a little bit of math and extra operations thrown in to help. We can give it a type and a default value plus some properties like range or the increment amount. And then when we want to add an extra property, it's simply a matter of adding a line to the schema and then referencing it later in the render. So there's a lot going on here, but basically we're just setting up these props on the left, and then the interpolated values come out on the right, which makes it really easy to use. We can use Deck to handle a number of our visualization projects. So in this example, we're showing a noise profile of our aircraft versus a common helicopter type. Because Deck natively speaks geospatial formats like GeoJSON and H3, we're able to drop in our data and spin up an application in a few minutes. Files are automatically geo-referenced for us and projected into model space. We can leverage all of the existing geospatial JS libraries like TURF to really highlight the messages we're trying to convey. And tools like Kepler.gl and Foursquare Studio are great for interactively exploring your data to get a sense of the stories that are available for you to tell. You gain a lot by being able to update values in real time and test hypotheses, gradually adding more and more layers of design to make your story clear. Data is like our paint. We draw on it on a canvas with Deck and move the brush with the ERJS. We can also procedurally derive filters. We can introduce elements one by one by using the index property that Deck gives us in accessor functions. Then using a delay or an offset value, we can bring in those bars one by one. Especially in the case of motion graphics, you often want certain properties like opacity or an outline to trigger based on an event or one by one or each after a delay following the previous. And it becomes pretty easy to keyframe here. Most filters tend to filter for a range of values, for instance, only keeping those within a min or a max, but a more advanced filter use case is a radial fall off, which are also more common in motion graphics and give a really nice, pleasing appearance because they're a little softer. The value is steadily ramped down from the center over a distance. In the range video, we faded in the cities one by one from the center, tying their opacity to a radius property with a bit of feather to smoothly bring in the labels. Though I think we can use a mask now. No, this is Shoji's talk. Often in 3D programs, this radius is represented by a radial gizmo. This is an example of a filter we were able to easily add to our project due to the flexibility. So given keyframes and times, the framework interpolates values that we use to construct state and state to construct the frame. Some of the more powerful parameters hook into data filters, joins, and aggregations, such as spatial cluster or temporal bins. Parameters can even hook into backend APIs to load tiles or retrieve remote data because the frame is blocked until all async actions settle. How state is created is totally arbitrary and up to you, and therein lies its power. So in summation, think less joysticks and more marionettes, less single variable interaction, and more chording and orchestration.
Lest you think these techniques are only good for rendered video, keep in mind that you can use them anywhere in a web app. Deck has this really nice fly to animation that implements this idea. But what if you were to tie these sorts of rich interactions into parts of your application? Say, clicking on a result in a list to flash a highlight around a point on a map. Or like this, maybe a guided tour through 3D scans of my backyard using a scroll bar as a trigger. This kind of interactive website, this kind of interaction is called scrollytelling, and I used this to create an interactive website to show the evolution of my landscaping project. Fortunately, thanks to Theater.js, this technique allowed me to define the keyframes and values down there in the editor interface and then seamlessly load it back later for playback without the editor and just wire up the scroll bar to the sequence's position, and then you still have that interactivity. So here I finish up by adding the opacity keyframes to fade in the finished backyard. I scroll to the place in my timeline where I want to start the fade in, and then click the triangle to add the keyframe, scroll to where I want it to finish fading in, and drag the opacity slider to create that keyframe. It's super easy, and it's really cool how you can just kind of combine all these different layers, techniques, HTML overlays, and Deck all in one to create this kind of like text, motion, scrolling interaction. So this isn't rendered. This was kind of like a real-time application that'll be online.
All right, let's talk video rendering. So to render a video, we call a custom loop with the timer as a trigger. We run our state operations to get eventual consistency in the recorded frame, and then capture that frame to a video container, then go to sleep and kick off the cycle again. We don't capture the frame until Deck is fully finished rendering, so that might be style tiles, 3D tiles, or models that it's drawing. After each render finishes, the canvas gets turned into a 2D grid of pixels and sent as a buffer to be encoded to the video container. The codec takes a raw frame and processes the image to reduce the amount of information stored. It also diffs the image from previously encoded frames to store only what is perceptibly changed in the video container. So this results in a much more efficient playback, smaller file sizes, and portability across devices. So in our case, we capture the canvas data as a stream and then use a reader to give us back a video frame. It's like Canvas to Blob, but a little bit faster. You can also call navigator.get user media to get a fully composited frame from the browser's render engine, similar to how screen sharing works. They're just streams at the end of the day. So modulo a few lines. This is actually the code we're using, and it maps pretty closely to the way that we first diagrammed it out, which has been pretty great. We loop over all frames in the sequence, wait for a React render to signal it's done, which is this frame ready promise here. And we then await the frame from the canvas's video stream, gives us back a video frame with pixels in BRGA format. From there, we can perform any video effects on the buffer, or in this case, just pass it directly to the encoder. The rest of the encoder looks like this and mostly just deals with writing to the file system and taking the frame we just encoded and adding it to a container. In the past, we've had to deal with the slow overhead of serializing and deserializing the canvas as a string, which incurs a pretty big overhead. And actually, a lot of libraries still do this, surprisingly. But thankfully, in the last year or two, the Web Codecs API landed in most browsers, which gives us the ability to use core media primitives, and it incurs virtually no overhead. We pass it a codec string, in this case VP9, to encode the frame, and a library called WebMMuxer is responsible for multiplexing the frames, so that is packaging them to a WebM or Matroska container, and that can be played elsewhere. It all works really nicely because we can just deal with streams and buffers everywhere. So to summarize, we have a render loop that is responsible for building state, rendering to deck, and then capturing the video container, and then sleeping until it's finished or done. I want to shift gears for a minute, talk about some future directions. We're looking to other packages like geometry nodes, Unreal Blueprints, Blender, or Houdini. We've been looking at a lot of alternative ways for creating our visuals. Low and no code formats. And we've been looking a lot to nodes. So this is an application called Data Blocks. This is a paradigm called visual programming language. The objects and operations are represented as nodes with inputs and outputs, which can be computed from and shared with other nodes in the graph. You can import arbitrary data blocks and switch between them. And the power is in the flexibility and how you can compose this, and non-destructively. So this is an example of an idea we've been kicking around for a while, which is bringing a visual programming language to deck. This is still super early, but there's already lots of potential. So we want to kind of combine the idea of these nodes with the timeline features and the ability to kind of define our nodes as a topological sort or left to right, and then upstream values can be memoized. You can think about it like the left sidebars from Kepler to configure layers, but lay it out as nodes and edges with the added dimension of time. There are lots of packages that support this. This is not a new concept, but there's a lot of really powerful ideas, lots of flexibility, and you can do things like create one-offs. Let's see. So this is Blender's geometry nodes. You can add in other nodes within this stream. Again, you kind of read it right to left or left to right. You can add in objects and wire them up, and then arbitrarily sort of remap your properties. So a big use case for us is swapping out data sets, especially for live versus offline data. But there's a lot of logic in the middle, that transformation that we do to that data. And maybe only some live data has certain transformations applied and some offline data has others. But being able to quickly iterate and try new things is a really big piece for us, and kind of create this idea of a recipe in the middle. Another thing that these give you is the ability to kind of package the nodes into groups, as Blender calls them, and then promote parameters that can be art directed, and we can hand off to people down the line. So someone who may not be familiar. So our kind of eventual goal with this is, an example of using effects within deck.gl that you can pipe into the output, and you can have multiple effects. We have like an ambient light and a zoom blur, which both go into this effects port here. And we want to start with using Deck's declarative JSON spec as a building block, and maybe think about this as a configuration interface for that. We're still very much in the early days of R&D on this, but if this interests you at all, we'd love to chat about it. And so lastly, and let me breeze through this stuff because Xiaoji covered a lot of it, but we're keeping a keen eye on WebGPU and Luma v9's support for WebGPUs. So for us, a lot of these render passes are really useful. So say ambient occlusion, depth, specular, normals, RGB, that sort of thing. And then we can write them to a format called EXR, which is an industry standard that allows kind of extra information tagged, and then bring it into a compositing software and really pull out specific things. We also want to look into USD and Material X for sharing with a lot of our architecture projects that people at our company use. And then finally, looking at a lot of in-browser databases and in-memory setups. And WebGPU unlocks a lot of this stuff for us, but also it's all research and all kind of directions we're doing to slowly grab ideas from tools like Unreal and Blender and kind of bring in those pieces.
And so by bridging the gap between a high-level UI and these lower-level APIs we were just talking about, we can make everyone happy. At least that's the thesis. When libraries aren't layering on friction and unnecessary abstraction, and instead bringing your interactions closer to good primitives, it becomes a lot easier and faster to make really rich and compelling experiences for your users. We hope you enjoyed this talk, and we'll give animation a try in deck.gl. Thanks.